Here is a problem that sounds mundane and turns out to be deep. You have an unstructured collection of items, and exactly one of them is the answer you want. Think of a phone book, but sorted by name when the only thing you know is a number. The order buys you nothing. Classically, there is no cleverness available. You check the items one at a time until you hit the marked one, and on average, that is half of them. With the symbol n standing for the number of items, Grover's algorithm finds the marked one in about the square root of n. Steps instead.
Wait, the square root of n, is that all? A square root is not even exponential. Why is anyone impressed?
Work it out though, say 1,000,000 items. Classically, that is 500,000 checks on average. The square root of 1,000,000 is only 1,000.
1,000 instead of 500,000.
That gap is the point. The speedup is quadratic, not exponential, but it is provable, and it works for any search you can phrase as spotting one marked item with no structure required. And the way it gets there is the real prize: interference. Steering amplitude toward the answer. Love Grover found it in 1996, and it remains one of the few quantum speedups we can actually prove. Let us watch it happen with the picture we have used all series: a row of amplitude bars. One bar for each item. The height of a bar is how much amplitude sits on that item, and the little arrow on top is its phase. Take 3 qubits, so 8 items. We begin the way we begin every quantum algorithm, by putting the register into a uniform SOR position, 8 bars of exactly equal height. Measure right now, and every item is equally likely. The marked one, item number 5, looks like all the rest. Grover's whole job is to grow that one bar and shrink the others, using nothing but phase. Grover needs 2 operators, and the first is the oracle. Think of the oracle as the thing that can recognize the answer when it sees it, the way you recognize the right phone book entry the moment you read it, without knowing in advance where it lives. The oracle knows which item is marked, and all it does is flip the sign of that item's amplitude. Watch the marked bar. Its phase arrow swings half a turn from pointing up to pointing down, and its amplitude goes negative. Every other bar is left completely alone. In code, the oracle is almost nothing, the identity matrix with a single -1 on the diagonal sitting at the marked index. That is the entire ingredient. One recognizer expressed as one sign.
Hold on, if it only flipped a sign, the bar is the same height just pointing the other way. And the probability is the height squared, so a minus sign squares away to nothing. Haven't we changed anything we could ever measure?
Exactly right, and that is the whole trick. Measure immediately after the oracle, and you would see no difference at all. Every probability is untouched. The information the oracle just wrote is hidden in the phase, not in the magnitude. By itself, a phase is invisible. Remember episode 3. Phases never change a single measurement on their own, and yet they are the resource everything else is built from. The second operator is the one that converts that hidden phase into real, measurable amplitude. That is where the magic lives. The second operator is called the diffusion operator. And it performs one beautiful geometric move: inversion about the mean. Take all 8 amplitudes and compute their average. Draw that average as a line across the bars, like a mirror lying flat at the average height. The rule is simple. Every bar will be reflected through that line. Whatever sits above the average drops by as much as it was above, and whatever sits below rises by as much as it was below. Written as a matrix, the diffusion is just as compact as the oracle, and on its own, it does nothing useful at all. The trick is what happens when the two take turns. Here is why pairing the 2 operators works. The oracle just pushed the marked amplitude below 0, which drags it far under the average, while the 7 unmarked bars all sit a little above it. Reflect through the mean, and the marked bar, being the farthest below, vaults the highest above. Watch it grow. The unmarked bars barely move, the marked bar leaps. One flip, one mirror, and amplitude has flowed onto the answer.
So the sign flip is what makes the marked bar stick out from the average, and the reflection is what turns sticking out into being tall.
That is it precisely. The oracle marks the answer in phase. The diffusion caches that phase in for height. Together, they are one round of amplitude amplification. Do it a single time, and the marked probability has already jumped from 1/8 to about 4/5. That is the engine of the whole algorithm. Mark in phase, reflect in amplitude, and probability drains from everywhere else onto the answer. Let us name the loop. 1 Grover round. Is the oracle followed by the diffusion? Flip the marked phase, then reflect about the mean. Watch a full round in one take. Down goes the marked bar as the oracle fires, and then the mirror catches it and throws it high above the rest. After a single round with 8 items, the marked bar already towers over the others and carries most of the probability. So we simply do it again. Run a second round. Flip the now tall marked amplitude negative again, reflect about the new, lower average, and the marked bar climbs even higher. After 2 rounds, our 8-item search puts about 95% of the probability onto item 5. Run it with more qubits and the same rhythm plays out, just with more rounds, the marked bar climbing a little with every pass. There is a clean geometric picture underneath all of this. Each round rotates the state by a fixed angle in a plane spanned by the marked item and everything else. Every round is one more nudge of that rotation toward the answer.
And in the real code, is this just a short loop?
Just a loop. Start in the uniform superposition, then apply the oracle and the diffusion the right number of times. In the from scratch package, it is a handful of lines. Build the 2 matrices, multiply them onto the state vector once per round, and measure. The whole algorithm fits on a single screen. No compiler tricks and no special hardware in the simulator. The same NumPy arrays we have used since episode 1, steered by 2 small matrices. Now the part that startles anyone coming from classical computing, where more work never hurts. With Grover, you can do too many rounds. Because each round turns the state by the same fixed angle, the marked probability rises, reaches a peak, and then, if you keep going, falls back down. You can over-rotate, sailing right past the answer and back into the noise. More is not better. There is a right number of rounds, and overshooting walks you back off the answer. So the skill is stopping at the top. The peak sits at about pi/4 times the square root of n, rounded down. That formula comes straight from the fixed rotation angle. Each round turns the state by the same amount, so the number of turns it takes to reach the top is set in advance. For 8 items, that is 2 rounds. For 1,000,000 items, it is a little over 800. That count, growing like the square root of n, is exactly the speedup we promised at the start. The whole algorithm is one slow, deliberate rotation, and the art is knowing when to get off.
All right, 1,000 steps instead of 500,000, provably, for any unstructured search. I will admit that is impressive.
Good, and notice what the speedup did not require. No structure in the data, no luck, only interference used deliberately. There is no army of parallel universes checking every answer at once. There is one vector being rotated toward the one you want. By phases, the oracle sets and the mirror caches in. That is the geometric heart of quantum algorithms, made visible. Next time, a different way to steer amplitudes, reading hidden frequencies with the quantum Fourier transform.